Today's topic is solids, liquids, and gases. And the big idea is that interactions at the molecular level really determine properties all the way down to the cellular level. So the idea here is that something called intermolecular forces really impact what phase something is in, the solid, liquid, or gas phase, and really the attractions that the molecules have for each other, and that will have a big impact on properties. So we have a glass of water here because water's sticky forces that hold one water molecule to the next are really important for water. At the cellular level, we have a picture of a cell, and then sort of zoomed in at the chromosome level, we have a picture of a DNA double helix. And the idea here being that, the double helix is kind of like a ladder with its two long, sides of the ladder and then rungs that are parallel to the ground and rungs that are running up the ladder. And so it doesn't matter so much what all of the details are on this DNA double helix, but the idea is that on the sides of the ladder, you have this molecular structure. And then the way that those sides of that ladder are stuck together, or kind of the rungs of that ladder, are actually not bonds, but sticky forces, these intermolecular forces. So the sticky forces that make the rungs of the ladder are called hydrogen bonds. They're a type of intermolecular force, and they're a really important one. They actually hold the water molecules together to each other so that they're a liquid at room temperature and not just floating away as a gas at room temperature. So that's really important to our everyday life. But if we look some more at the DNA and we just try to get the big picture idea, the two sides of the ladder are going to be made up of these nucleic acids. The gist of the nucleic acids is that there are these 5- and 6-membered rings. We see those a lot in nature that are carbon-based, and they're heterocycles where they have some other atoms in the ring. We're seeing a lot of nitrogens in them and some oxygens. So that's just the big picture to keep in mind. And then what happens is one side of nucleic acids is stuck to the other side by, we see these little dotted line sticky forces holding a hydrogen on one side to a nitrogen on the other, or a hydrogen on one side to an oxygen on the other, and those are called hydrogen bonds. And those hydrogen bonds are those sticky forces, those interactions between the nucleic acids on one side and the nucleic acids on the other, really keep that double helix stuck together. So it's actually not a bond that does those rungs, but this sticky force, and that's super important. So we want to learn some more about not only phases, but how these sticky forces impact phases and then impact all sorts of other cool properties that we need in everyday life. So again, the bonds were the solid lines, like nitrogen covalently bonded to hydrogen. So we have our solid line bonds, and then we have our intermolecular forces, or IMFs, and those were the dotted line interactions, and they have a big impact on everyday life. So before we can dive too deep into IMFs, we're going to just review a few things about phases and phase changes. We're going to review melting and boiling points. So we've got a thermometer here that's labeled from -50 all the way to 100 degrees by 10 degrees at a time. And then we've got the freezing point of water labeled at 0 degrees Celsius, room temperature labeled at about 20 degrees Celsius, body temperature at 37 degrees Celsius, and the boiling point of water labeled at 100 degrees Celsius. So when we talk about phases and phase changes of water, we talk usually a lot about freezing and boiling. I'll put them on there in Fahrenheit too, just because we see that a lot in the news and everyday life, that freezing point of water is 32 degrees Fahrenheit and boiling point is 212 degrees Fahrenheit. I suppose I could have put body temperature in Fahrenheit. Most of us are pretty familiar with that one. It's 98.6 degrees, in Fahrenheit, but we'll leave our Celsius on here for now. Let's focus on melting and boiling point. First of all, if water boils at 100 degrees Celsius, we could also say that it evaporates or it vaporizes. Those are all synonymous. They mean the same thing. We're talking about liquid going to gas. That's also the temperature that water condenses at and gas goes to liquid. It's like two sides of the same coin. It's got the same value. You know, coin is always worth the same value. This is our 100-degree coin. And on one side, you could be talking about boiling, evaporating. On the other side, you could be talking about condensing. It just depends on if the energy is added in or being removed. At the freezing point, you're melting. Solid's going to liquid at 0 degrees Celsius, but you can also freeze it and liquid can go to solid. So both of those phase changes happen at 0 degrees Celsius, melting and freezing. It's just a matter of if energy is going in or being removed. So to boil or evaporate, we have to put energy in, and we learned that energy in was endo. So that's going to be an endothermic change. Just like for melting, energy has to go in. That's going to be an endothermic change as well. Whereas if you're trying to condense the water, you're going to have to remove energy from the gas. The energy is going to have to exit the gas, in order for it to condense and become a liquid. So that'll be exothermic. Just like to freeze your liquid, energy is going to have to exit that liquid. So that's going to be exothermic. So we can apply those endo and exo terms that we studied in terms of energy. At the bottom of the screen here, I've got a little box for solid, and then one for liquid, and then one for gas. And then arrows going back and forth, an arrow from solid to liquid and liquid back to solid. And in the middle, that liquid has an arrow over to gas and from an arrow from gas back to liquid. So my point here is as we go from solid to liquid, that arrow would have plus heat, right? You have to add heat energy in. Just like to go from liquid to gas, plus heat, we'll have to add heat energy in. And if we're having to add heat energy in, then these processes are endothermic. And if we go from gas back to liquid, we have to minus heat, or we're removing heat. And from liquid to solid, also minus heat. We're removing heat, so these are exothermic processes where heat is having to exit the system or be removed. So that's the idea there, that we have an exothermic process then. Let's take an example. Sometimes we get examples where we're supposed to sort of imagine, let's imagine that we have a substance and perhaps let's say it has a melting point of -400 degrees Celsius. That might seem outlandish, but that's possible. And then let's say it has, let's say it has a boiling point of, okay, so this is going to be its melting point. Let's say it has a boiling point of negative, I don't know, -35 degrees Celsius. And then what if the question is, what is the phase at room temperature? So I want to know, what phase is this in at room temperature? Well, I need to recall that room temperature is about 20 degrees C. Okay. And then I need to kind of think of it. Well, okay, anything below 400 degrees, -400 degrees C, by the way, is going to be solid. If it's between -35 and -400, that's when it's going to be liquid, somewhere in the middle here. And then it's anything warmer than -35 degrees C is actually going to be a gas. Well, if I'm at room temperature, I'm certainly warmer than -35 degrees C. And so the answer to this one is that it's actually going to be a gas at room temperature. If its boiling point is -35 degrees C, by the time I've gotten up to room temperature, I've definitely given this enough energy to boil. So that's how we could ask an example about phases and phase changes.